Hey guys, welcome back. Today we'll look at subspace. So let's see what is a subspace. Suppose that we have a vector space VF. We are writing this representation of vector space. Here F is field over which the vector space is defined, and we already know about the field. And there is a subset S of the vector space. So what do we mean by the subset of vector space? So vector space contains vectors basically. It's a collection of vectors. Okay. So if the subset of this collection, if we take subset of this collection, it will be the subset of V vector space. Okay. So let's say that S is a subset of V and S is non-empty. Now, if S is a vector space itself, obviously the operations that are present here in our vector space, let's say the operations are addition and our usual multiplication operation, and if S is a vector space with these two operations, if S plus and this multiplication operation is a vector space on its own, then we can say that S is a subspace of vector space V. Okay, so this is a trivial condition. But if you go with these conditions, like S is non-empty, and then you start proving that S is a vector space on its own, then you will have to prove those. You will have to show those 10 conditions, 9 or 10 conditions that are this algebraic structure should satisfy in order to be a vector space. It's kind of a lengthy process. So we have 3 necessary and sufficient conditions, and let's see what are these conditions. So first thing is we have S non-empty and S is a subset of V, right? After that, if any one of these 3 conditions, is satisfied, then we can say that S is a vector subspace of V. Okay, so condition 1, it is known as two-step test because it has 2 components. What condition 1 says? That if for all A and B vectors of S, A plus B also belong to S. Okay, so first condition is for all A and B, if we take any arbitrary vectors A and B from S, then there should be a vector that is A plus B that is also in S. Okay, the second condition says that for all vector A from S and an element from the field F, we have the element multiplied by the vector in S. So you can see that for any arbitrary element, for any arbitrary vector of S and an element of F, we have the multiplication of these 2 elements X and A in S. So if these 2 conditions are satisfied, then we can say that our S is a vector space. So this is known as two-step test. Why it is known as two-step test? Because it has two steps, 1 and 2. The second one is known as one-step test. And basically when you'll solve the examples, we'll see, then we'll be using this one-step test because it saves little bit of time. So this says that for all vector A and B in S and element X and Y in field F, we have X multiplied by A plus Y multiplied by B in S. So if we take any element, any arbitrary element A and B, and we take any element X and Y from our field F, then we should have an element that has some sort of representation like this: X dot Y, X dot A plus Y dot B, and it should be there in S. Okay, so this is the second condition. Third condition is little bit simpler. So if we have any two vectors A and B from S, and we have a single constant, single element from field F, and corresponding to these elements we have a vector X dot A plus B in our set, in our subset of V, then we can say that our S is a subspace of our vector space V. Okay, so there are three conditions. I'll repeat, these three conditions are there. Okay, and any one of these three conditions, if any one of these three conditions is satisfied by our S, that is subset of V, then we can say that our S is a subspace. Okay, I hope you got it, like somehow you got some idea, right? So let's see some example. Okay, so suppose R is our field. Okay, let's take a bright color. R is our field, and we have our vector space as V3R. So don't be afraid about this V3. It just represents that our vector space is three-dimensional. Okay. So what will be the element of these vectors? So our general element will be like X comma Y comma Z. So it will be an element like arbitrary, a general element of V3, right? Where these X, Y, Z, they all belong to the field. Okay, so the elements of the vectors or the entities of the vectors that are present in our vector space. Okay, so the element of those vectors will be from the field. Okay, so let's see here. So R is our field, real numbers, and we have our vector space. We need to show that this particular set is a subspace of V3. Okay, so we can easily see that the general elements will be of this form. So we can say that whatever the elements that are contained here will be there in our V3, right? So easily, if we take it as S, then we can say that S is a subset of V, right? So, if you want to see it clearly, we can see that if X belong to R, Y belong to R, and Z belong to R, then we can easily see that 2y will also belong to R and 3z will also belong to R, right? So in this way we can see that x comma y comma z, if this belongs to V to V3, then we have another element, that is x, 2y and 3z belonging to V3. And we already know that our V3 is just a vector space of 3 dimension, no further condition. Okay, these are the arbitrary elements. So if they are in V3, then this will also be in V3. That means that our S is a subset of V, and S is not empty, right? Okay, like if R is the real number, set of real number, and we are taking these elements from the set R, then there will be some elements. Okay, so S is not a empty set, right? If you have any problem, you can just ask me in the comments. First thing is clear, that S is a subset of V. Now what we need to prove some conditions. So what I'll do, I'll take this one step test. So all these 3 conditions are necessary and sufficient conditions. So you can take any condition, and if the condition is satisfied, then you can say that S is a subspace of V, right? So I'm going to take this single step test. So what the single step test tells us? It says that for all A and B vectors from S and X and Y elements from F, we should have X dot A plus Y dot B in our set S, right? So let's see, if we have 2 vectors V1 and V2 from our subset S, then we can write V1 is equals to x1 2y1 3z1, right? And we can write V2 equals to x2 plus comma 2y2 comma 3z2, right? After that, let's suppose the elements of F we are taking A and B, or let's say that T1 and T2 are elements of F, then T1 into V1 will equals to T1 x1 2 into T1 y1 comma 3 into T1 z1, right? Similarly, T2 v2 will be equals to, right? And we need to show that this t1 v1 plus t2 v2 belongs to S. So if we can show that this particular element is nothing but a form of x, 2y and 3z, where x, y and z belongs to R, then we can say directly that okay, this particular vector is from S, and then we can easily say that our one step test is satisfied. So we can say that our S is a subspace of V, right? Okay, so let's see. On adding it, what we'll do, just add t1 x1, 2t1 y1, 3t1 z1 plus t2 x2, 2t2 y2, 3t2 z2. Okay, what it will give? It will give, right? Now we know that t1 and t2 are from our field, okay, real number. So we have taken our field as real number because it is already given here, okay. You can see it's given here. It's given that R is our field, right? R is our field. So we know that T1, T2 are from R, okay, or our field, and we know that x1 and x2, y1 and y2, z1 and z2 are also from R. And from the properties of real number, we know that if t1 and x1 are from R, then t1 multiplied by x1 will also be available in R. It will also be present in R, right? And we know that, so from this statement we know that this is also in R and this is also in R, okay. And we know that if two real numbers, adding any two real numbers will always give a real number, right? So we know that if this is a real number and this is a real number, from this condition, as we know that if t1 is there in R and x1 is there in R, so their multiplication will also be there in R. So these two numbers will be in R, and adding, so these are the real numbers. If they are present in real number set, then obviously they are real numbers. So adding two real numbers will always be a real number. So we can say that this is a real number k, right? This is a k. Similarly, this will be in real number, this will be in real number, and this, adding these two will be in real number. So we can say that it is j, so 2 into j. And similarly, same logic applies here also. So we can write is 3. Let's say that we can write it like maybe p, okay. And this is actually a form of this, and here k, j, p are all from the real number, right? So we can say that this k, 2, j, p will be there in S, because S contains the numbers of this format, and this number is itself in this format. So we can say that this element is there in our subset S. So if it is there in subset S, then a step test is satisfied. So it means that S is a subspace of V. Okay, V3, right? So this is a very trivial example. I hope that you have got the understanding from this video what are subspaces and how we can test these subspaces, whether they are a subspace or not. So